Welcome to Unit 5. We're getting closer and closer to the end of the school year, and Unit 5 is going to be different from any unit you've seen so far. It's all about counting and probability, which I think you'll find pretty interesting. Our first lesson, 5.02, is about sample space and events. So let's take a look at our goals. Determine the sample space in an experiment. Very soon, you're going to learn what a sample space is. An experiment will look something like spinning a spinner or rolling a dice, something like that. We'll also need to determine the number of outcomes in a sample space and determine the number of events that result from unions, intersections, or complements of other events. So what is a sample space? This is the most basic example I could give you. If you flip a coin, the possible outcomes are heads or tails. That's a sample space. Simple, right? So the bottom line is a sample space is a set of possible outcomes of an experiment. So if you have a coin, like a quarter, let's say, you flip it, you can only get heads or tails. Those are the two possible outcomes, right? Of course, you could continue to flip that coin over and over, but those are still your only possible outcomes. Now, the sample spaces we're going to look at will be a little more complex than that, but nothing to worry about. I'm going to guide you all the way, and the set may be represented by a list, a table, or a tree diagram. Today we're going to really work with tree diagrams. So let's take a look at this spinner, and we're going to imagine it's spun twice. So if you spin this one time, what are your possible outcomes? 1, 2, 3, or 4, right? So on the right side here, you see this tree diagram, and that's exactly what's happening. This column represents the first spin. You could spin 1 through 4. But in this example, we're being told the spinner is spun twice. It's the same spinner. So are the possible outcomes going to change the second time? No. So we're going to list those out as well. But why does this look different? Well, these values represent the second spin given that the first spin already took place. Okay, so what you're looking at right here is a tree diagram. Your tree diagram can be sideways like this, or it can go top to bottom like this. It's up to you. But really, ultimately, you need to think about for a second what's really going on. What's really going on is, well, you could spin a 1 and then a 1. Let's get a color that stands out just a little more. Let's see. You could spin a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, a 1 and then a 4. But if you landed on a 2 the first time, you could spin 2 then 1, 2 then 2, 2 then 3, 2 then 4. Maybe you land on 3 the first time. You could spin 3 then 1, then 2, then 3, then 4. You get the idea, right? So what we've done in this tree diagram is listed all possible outcomes. We're not even finding probabilities yet. We will. But for now, we're just focused on putting together a tree diagram to show everything that could possibly happen if we spun this spinner twice. And when you're asked to, which you will be asked often, to find the number of possible outcomes, that includes every value in the last column or row of information. I say column or row because, again, you could have your table drawn this way, where we'd have 1, 2, 3, right? Like this, 4. You get the idea. Okay, so you could look through all these and count. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Da, da, da. That's pretty tedious, though. It's quicker to use multiplication to work smarter, not harder. Here we have 1, 2, 3, 4 groups of 4. So we can multiply 4 times 4 to find out there are 16 possible outcomes based on spinning this twice. Now, let's see if you can draw your own tree diagram. A family wants to have 3 children. A tree diagram is what we need to create for this sample space of outcomes of children by gender. So, of course, we're talking about babies here in this example. Can you do it? Try. So what is the first possible option? Well, the first baby these aspiring parents could have is a male or a female. You can put B or G, boy or girl, male or female, whatever you prefer. Well, if they had a male or female the first time, what could they possibly have the second? The same thing, right? Again, we're not talking about how likely it is to happen, which is probability. We're just listing the possibilities. And then third baby, of course, same possibilities, right? There it is. And that was question A. Question B asks us, how many unique birth order outcomes are there by gender? Well, these are all unique, right? Because you could find, you could have a boy, then a boy, then a boy, right? You could have a boy, then a boy, then a girl. That's unique. Those are different. Boy, then a girl, then a boy. Boy, then a girl, then a girl. You get the idea. So how many? Well, once again, it's all about how many are in that final row. How many do you see? Well, I see 4 here and 4 here. So we have 4 times 2, there are 8. But what if there's 2 spinners that are different? We can handle that, can't we? Let's do it. Okay, the spinners on both dials we see here are going to each be spun once. So first, we spin the first spinner. What are the possibilities that we'll land on? Well, 1 through 4, right? And I would recommend always spacing these out to give yourself plenty of room because you don't know. Are they going to be small trees or big trees? We'll see. So first spinner is written out. And then what happens on the second spinner? Well, we could land on a 4, a 5, or a 6. So we'll have 3 branches on each tree. And I know it seems a bit redundant writing this over and over, but this will really help you visualize what's going on to answer the questions you'll be asked. And there are a few questions we'll be asked in just a moment, but we really need to get a good understanding of what's happening down here. There is a big difference between the word and or in this unit, and I would highly recommend writing down what's in this red box. The word and means it must meet both requirements. So this is a little more of a strict situation. The word or is a little more loose. It means that at least one of the requirements are met. This can mean both are met or just one of them are met. Let's answer some questions to really get a grasp on what's happening here. So here's question 1, here's question 2. First, determine the number of possible outcomes that show a 2 on the first spinner and a 6 on the second spinner. Where do you see that happening? Well, I only see a 2 on the first spinner right here. And both things need to be true. So I need a 2 on the first spin and a 6 on the second. Are there any other situations here where we see a 2 on the first spin and a 6 on bottom? Both things happening together. 2 and a 6 match? No, that is it. So that means there is only one possible outcome for that situation. Now, a second ago, I talked about how and or makes a big difference, and we're going to see that right now. This is the same exact question, but with the word or. So how many possible outcomes show a 2 on the first spinner or a 6 on the second? Okay, well, here's a 2 on the first spinner, and how many things can happen there? You could spin a 2, then a 4, then a 5, then a 6. So here, there are three possible outcomes. And how many more possible outcomes? Well, a 6 on the second spinner. I see 1, 2, 3, 4 sixes. So we have 3 possible outcomes plus another 4. Wait a second. What about this 6? Are we going to count that twice? We're actually only going to count that once. So 3 plus 3, 6 possible outcomes. Okay, remember our goals? Talked about unions, intersections, and complements. Well, it's time to learn about these. And I know at first glance this looks long and complicated, but it's really not if we take it one step at a time. Let's start off talking about unions. The union of two sets of data, the union of two sets is the set of all elements in either set. This is a very welcoming set, unions. It's saying, come one, come all. If you're in either situation, we want you to join us. And that is indicated by this big U. Remember, U's with domain and range, same idea here. Now, A is representing one situation, B is the other. It could be spinning a dice. It could be winning the lottery. It could be whatever you'd like it to be. Okay? Rolling a dice, spinning a spinner, whatever you'd like. We're just going to say it's a spinner since that's what we've been looking at. So spinner A, we could say has a 0, a 1, and a 4 on it. And spinner B has a 1, a 2, a 3, a 4, and a 5. Well, the union of sets A and B will include all of the values from both. So ultimately, what you're doing is you're going down the list and you're saying, hey, what's the lowest value? 0? Put it in. Then there's a 1. Put it in. There's also a 1 here. Notice we only write it once. You might want to make a note of that. Then there's a 4. Okay, we'll put the 4 in. Then what else is over here? A 2, a 3, already listed 4, and a 5. So we've put everything here in this united set. What about intersections? Well, intersections means the elements occur in both sets. This is a more VIP situation, you could say. Think about maybe the solution to the system of equations, right? It satisfies both. So we're looking at this notation. It looks like an N maybe, or an archway, or that U flipped upside down. And we only want the values that are in both. So there's a 0 here. Is there one there? No, we're not going to include it. Is there a 1 here? Yes. 1 here, there? Yes. Let's bring it in. Got past security. All right, what about 4? 4 is there. 4 is also there, so that is included. And we've gone through every value in A, so there's no need to look at any other values in B. And finally, what are complements? Well, the complement of an event is just the event that's not occurring. And you might be wondering, why do I care about a value that's not occurring? Well, maybe if it's not an ideal situation, like losing $5,000, losing your job, dropping out of college, bad things, right? Maybe we want to know the probabilities so we can avoid them and maybe reduce that chance if possible. Here's one example, the complement of rolling a die and getting an even number is let me just read it. The complement of rolling a six-sided number cube, a die, and getting an even number is rolling a six-sided number cube and not getting an even number, so getting an odd. Okay, that's enough about unions, intersection, and complements. Now it's time for a little word problem. A quilt is made of 48 large squares. Pretty good sized quilt, right? Patrice has the 48 squares ready to sew and sorts them. 12 of the squares have yellow stripes. 9 have green polka dots. 9 have red stripes. 6 have green stripes. And the remaining squares are red plaid. How many of these squares are neither red nor polka dotted? Go ahead, please, and try to see if you can point out all of the squares that fit this requirement, neither red nor polka dotted. Okay, let's go through the list. 12 are yellow and stripes. That fits the requirement. 9 have green polka dots. No, polka dots. Don't want it. 9 have red stripes. They're red. Can't have it. 6 have green stripes. Yes. And the remaining are red plaid. That would mean they're red. It doesn't satisfy this. So what do we do with these values? Add them together. 12 plus 6 is 18. Now we answered the question, but let's start talking about probabilities. How likely is something to happen? So let's just say Patrice is feeling adventurous and she's just like, I'm going to throw all the squares in a bag or a hat and I'm just going to pull them out at random. What would the probability be that one of the squares are neither red nor polka dotted? Well, you take however many that fit that requirement and divide it by the total. We were told there were 48 squares. And then we can simplify that if possible. I believe this is 3/8. You can go on your calculator to double check that, but that is correct. And probabilities are also nice because we can see percentages. So if you want to divide that on your calculator, you could see it's 37.5%. Those are both the answer, just written in different ways. And we have 2 more examples to practice and work through. A change purse contains 5 coins, 1 quarter, 2 dimes, 1 nickel, and 1 penny. 2 coins are selected randomly, one after another. How many of the possible outcomes are worth 15? Let's highlight this. Are worth at least 15 cents and contain at least 1 dime. It needs to satisfy both of those requirements, right? That's what and means. So a quarter, 25 cents, a dime, 10, nickel, 5 penny 1 cent. Okay. Creating this, what I've done for you, is already a project in itself because you're given these specific values. So you would need to go, okay, I have a quarter. If I have a quarter, what's left? Okay, I have a dime, but there's also another dime. So D1 is dime 1, D2 is dime 2. Then I have a nickel and a penny. So notice what's in the boxes changes from situation to situation. Now, I would recommend drawing this out as a tree diagram, but I did it this way to help you check things off. So I'd like you to pause this and see if you can figure out all of the options that fit this requirement. Keep in mind, the yellow boxes is the first coin that's selected. What's in the blue boxes is the second coin selected. There were only 2 selected. And they're one after another, so you can't pick the same coin twice. Let's see how you did. These are the correct answers. Did you get them? I hope so. I'll just point out a few situations to help you understand. If I pick a penny then a quarter, no dime was included. If I pick a penny then a nickel, no dime was included. Penny and a dime is 11 cents. Penny and a dime is 11 cents. That's why nothing in this box was checked off. Dime and a quarter, that is 35 cents, and there's a dime included. Dime and a dime, there's at least 1 dime included, and that is 20 cents, which is over 15. Dime and a nickel is exactly 15. Well, remember it said at least 15, so we'll take it. You could look through the rest and verify, but we want to answer this. How many? Well, we need to add up all of the checks, and you'll see there are 10 in all. And our last set of questions for the day. Quincy performs an experiment in which he flips a coin 2 times and then spins a spinner with 4 equal sections labeled 1, 2, 3, and 4. Okay, we haven't done this quite yet. How many possible outcomes are there? We don't know yet. We'll need to come back to that. How many outcomes do not include a spin? Okay, so these are all great questions, but we kind of need our tree diagram first, right? So let's draw it out and see what happens. If you'd like to pause and test yourself, I highly encourage it. But we're told what happens. First, he flips a coin 2 times. 1 coin, so heads or tails. And then he flips it again, heads or tails. Then what happens? He spins a spinner with 1 through 4 on it. How many times? Just once, right? So over here, we'll have 4 options, 4 options. Each one of these, right? 4 options. 1, 2, 3, 4. Now we can answer these questions a little bit better. A lot better. How many possible outcomes? Well, we have 4 sections of 4, right? This bottom row, 16 possible outcomes. How many outcomes do not include a spin of 2 or greater? 2 or greater. Let's think. I see H1, right? If I go from H to H to 1, I do not get 2 or greater, right? Which others? Do you see them? I see H heads tails 1. right? Over here, heads, tails, 1. So I'll just keep these drawn out for the moment. Heads, heads, 1. Heads, tails, 1. What else? Tail, heads, 1. Tail, tails, 1. Right? So every pass that ends in 1. That's essentially what we're doing. Let's write it out. Tails, heads, 1. Tails, tails, 1. That is 4 outcomes. How many outcomes have at least one head? I would say a lot of them, right? I would say at least one head. While we know every option here has to have at least one heads because it started with it, right? So we're going to be looking over here, but on this side, there is heads right there. So what we're really doing is we're looking at these options, tails and then tails. There were no heads, right? When he flipped the coin, no heads there. So what did we have? We had a total of 16 possible outcomes, and we're going to subtract however many don't have a heads, which is 4, so 12. And finally, last question for the day. How many outcomes have at least one head or, keyword or, an even number on the spin? Okay, how many outcomes have at least one head? Well, didn't we just calculate how many? We just did that, right? 12. How many outcomes have at least one head? So 12. But remember, or means you're combining possible outcomes. What's the other situation? An even number on the spin. An even number on the spin. Even numbers. Let's take a look. We have 1, 2, 3, 4, 5, 6, 7, 8. But are we counting all of those? No, right? Remember, we already counted all of these, right? These all have heads, so we're not counting any of those. We're only counting the 2 here, right? So plus 2 is 14. And that, my friends, is it for today.